like sitting down, though, right? Didn't John made it look good? Well, it's good to be here. Want to just talk a little bit about what we're doing in the space, what we're seeing in the space, and then ideally have some time for questions as we go on. Quantinuum is, we celebrated our 1-year anniversary last week. So we're not typically saying where our heritage came from, but I think most people know, right? We are the combination of Cambridge Quantum Computing and Honeywell Quantum Solutions into a single organization. We're about 500 people now. And one of the things I know I'm hearing is that the need for this to be a global ecosystem is critical. You know, the people, the human resource is the scarcest resource in quantum computing, and finding the best people to be working on this challenging problem, to be working on this exciting field, it's very hard to do. You really need to go everywhere to be able to get that kind of insight. And so we have locations in Japan and Germany, across the UK, across the United States, and we've been growing at about 45% in terms of our people over the course of this year. So it's been just a great time to be able to come together and make progress here. We also operate in what we call a platform inclusive way. So yes, we do have our own hardware, but we're actually one of the largest users of other people's quantum computers in the world. Why? Because we have 500 people that know what to go do with a quantum computer. We've built a integrated company, an integrated stack for a reason, and that is it takes a lot of work. It takes a lot of work to try to go make progress. Thousands of hours of compute time to be able to go and ensure that what you're working on is seeing the progress that you thought you were going to go do. You know, taking problems, fragmenting them down into the size and shape that we can run on today's quantum computers, and be able to have some legitimacy of being able to scale that as these quantum systems scale. But by doing that, we also can take advantage of things that quantum computers do today on their own. And by doing that, we've built out core capabilities around certain areas: cybersecurity, chemistry, what we call compositional artificial intelligence broadly, and machine learning specifically. And all of that is underpinned by an operating system layer that we use ourselves, our customers use, and we made open source to the world to have developers from around the world start to take advantage of how do you simplify what you're trying to go do and run it on today's quantum computers. So we're very proud of that. What's happened as a result is that we can start to put out tools in the world that people can take advantage of. And when they take advantage of that, they learn and we learn. And it's a boost to the entire ecosystem. So using something like Ticket, our middleware, which is a optimizer. So if you're developing quantum algorithms around the world, you can use Ticket as a way to be able to ensure that it uses the fewest resources, and it makes it portable. So yes, we've designed it so it works very efficiently, effectively on our own H-series, but it works on a whole host of other quantum computers. So you can make sure that you don't have to rewrite these over and over again. We have a tool out in the world for quantum natural language processing called Lambic. Again, open source to be able to have as a library and toolkit for people to look at how do you take advantage of this particular capability as quantum computers scale. So we're thinking about what do we go do in the short term, but this is going to be a long-term play. So how do we take advantage of some of the things that we think quantum computers are going to go do well? What they go do well is they act as quantum computers. So yes, can you simulate our current H1 generation with a laptop? You absolutely can. But people forget, when you're doing that, you're simulating the quantum computer in your classical computer. You're not actually entangling anything. You're not creating a superposition in your classical computer, but we are doing that in our quantum computer. And what does that do? It creates something that you can do right now that the world can take advantage of. And so we have that as an offering that's in the market right now. We have customers who are using our quantum computing enhanced encryption keys, quantum computing enhanced certificates, to make their entire cyber ecosystem more secure. That is something that you can only do using a quantum computer. You can't do that classically. That's where we are. We also work with our customers, we work with our own team to figure out where is the future of quantum computing going to go. And so do we believe in a future where you can start to look at developing molecules, really simulate how their interactions are with other molecules, what the binding energies are? Of course, we believe in that future. Are we there right now? No, we're not there right now. So how do you prepare to get there? You develop software that helps a tool to be able to provide computational chemists the ability to take their problem and shrink it down, take their industrially relevant problem and shrink it down in a way that they can fragment it and run it on today's quantum computers. Again, because you can't simulate that classically? No, you can. But it helps understand what that tool is going to look like as these quantum computers evolve. In fact, just yesterday, AWS released a statement, and we amplified it today, where work that we were doing with AWS Bracket and BMW Group on taking Enquanto and being able to look at these industrially relevant problems by fragmenting them down and running them on quantum computers using classical resources as an additional simulator tool. Those are things that we can do right now. How do we do that? Because we have a lot of people in the world helping us out. If you would have asked me 18 months ago, are there going to be 1 million people in the world that are able to go do quantum computing algorithm development? Absolutely not. I don't know where they're coming from. But this is 800,000 downloads, and we've gone into these universities. We've seen where there's 30 and 50 students all using the same system that has downloaded Ticket to be able to start doing quantum algorithm development. This is a generation of people who are so inspired by this technology that they're willing to just start practicing, start figuring out how they can take advantage of this entire industry as that evolves. It's incredible. And every time people use it, we get to learn. We get to learn as a company, but we get to learn as a community, and we're bringing that into our offerings. We're bringing that back when we partner with our customers and our channel partners. Now, yes, we also have hardware, and yes, we have a roadmap that we've talked about before on how we think we can go from where we are today to larger and larger scale systems. We absolutely believe in that process. We believe in that roadmap. But one of the things I wanted to talk about today is we do have a hype problem, and it somehow continues to get into that hype problem. And why do we get into that hype problem? So there are companies, I know, because we're one of them, where we spend the time trying to figure out how do you continue to increase performance? Because I agree with Dr. Preskill, it is going to take high-quality qubits to make progress. That's what it's going to take. Not just more, but really, really high quality. So we've taken an approach that says we're going to add qubits, we're going to increase fidelities. We're going to add qubits, we're going to increase fidelities. That's how we believe that the entire community makes progress. What happens, though, is I have had conversations like this. I'm sure any quantum computing people in the audience who are trying to explain to other people the power of quantum computing have had this kind of a conversation that says, what is this power that comes with quantum computers? Well, it's because to be able to simulate them, you start to have values in your classical system that increase exponentially, right? 2 values with just 1 qubit, 1,000 values with 10 qubits. And incredibly, you get into this 1.1 quadrillion value regime when you get to 50 qubits. But that's not the way it's happening. Because people then stop that conversation. They say, well, actually, this really depends on noise, right? This really depends on your error rates. Otherwise, it doesn't really work this way. And so as we are collectively as an ecosystem scaling, there is something else that we have to focus on, which is quality. Repeatability. That has become just a hallmark of how we try to present ourselves both in the ecosystem to our customers, with our partners. It is about being able to both replicate what you do every time, not making a hero run, replicating it every time, and when you do that, also making steady progress. That's why we made the challenge. This wasn't a challenge. This wasn't a boast to the community, to the ecosystem, this was a challenge to our own company. This is what we set as an audacious goal for ourselves, that we're going to continue to increase the performance of our system by tenfold every year for the next 5 years. That's what we set as a challenge to ourselves. I mean, I know many of you try to do the same thing, and you just imagine the beginning of a year, right? So the beginning of 2022, we sat down and we had in our company 5 different milestones. A milestone with a date, where the milestone was either first of its kind in the world or a world record. That's insane. Who does that? That's like saying to Usain Bolt, you know what, on May 30th, you have to get a world record. It works, though, but it only works one way. It works one way, and that is nobody can ever go under the bus. This is hard. This is really hard to do what we are all collectively trying to go do here. You have to take audacious goals. You have to make them, but then you have to have a methodology for how you're going to go get there. And incredibly, we've been on that drive. Now, what does that do? When you can go do that kind of performance increase, what does that do for the ecosystem? It provides an avenue to be able to actually make progress. Thinking about real quantum systems working like they do in real life, then how do you take what they do well and blend that into today's views around chemistry? Or challenging yourself to go, well, you know what, there are topics that are very hard for classical computers to do, really hard for classical computers to do. Is there a way that we reframe what that advantage looks like? What that computational advantage looks like, what that time advantage looks like, potentially even what that energy savings advantage looks like, right? It turns out these are very energy advantage systems, quantum computers. It allows us to make progress on products, getting actual products into the market where computational chemists in this particular case can use them and try to figure out, how do I get another tool in my tool belt? Because we're just at the start of this technology development, and as we grow, you want to know how to take your problem and transform it into something that a quantum computer can help you with. So that's what this does. It does allow us to do some really incredible things. When you make progress, especially when you make progress on high quality, when you have control systems that are incredible, you can do some incredible things. Dr. Preskill said earlier, this was a first, not just for us, but for the world moment to be able to say, you know what? You can actually entangle 2 logical qubits. You can start to see that the logical error rate is better than the physical error rate. Now, is it because this is the answer, this is what all quantum computers are going to do? No, but if you're talking about any quantum computer that is going to be universal, fault tolerant, it has to get to this kind of regime. You have to be able to get to the point where you're doing this kind of quantum error correction. So it provides a platform for people to actually test error correcting codes. Does this work? Is this matching what we theoretically thought possible? And our customers being able to take advantage of today's quantum computers to think about where they're going to apply these in the future. So this is JP Morgan Chase thinking about things like natural language processing. How do you look at your just gigantic store of contracts and figure out what's in them in a meaningfully fast way? This is all happening because we have tools now that, yes, you can use a classical computer to simulate them, but they're really incredible. And they're growing in terms of their performance exponentially, and very fast exponentially, in this cadence, in a time frame that now starts to be pretty relevant. So what does that look like? If you look at just broadly at this timeline and say, well, if you have any chance of doing this at all, then your second generation must be close, right? It must be there. Well, you'd think so, right? It would have to be there. It is there. Now, why haven't we released it to the world? Because we have a really high bar for ourselves. We want to be the company that says, this is what it does. Here's the data that goes along with it. Here's how it works. And so when we are at that point, and we are very close, we are using this ourselves, but when we are at that point, then yes, absolutely, we will make that available to the public in terms of this is how it works, this is the data that supports it, and we'll make it available to our customers. But this is the kind of progress that's happening when we all put our minds to it. So thank you for giving me the opportunity to talk today. Now I have a few minutes for questions. I have a question there.
So I assume with H2 you will start out with a smaller number and keep adding ions to it up to a larger number. Can you tell us the ranges that you think you'll be able to operate with?
Sorry, that was about the second generation? Okay. That's always a question, right? So why don't we say what the numbers are? Is it going to be more qubits? Yes, it's going to be more qubits. Why haven't we said? Because we will say exactly when we know how many it's going to be that we'll release it. What I will say is this. It has the capability of having multiples more than our first generation. We have designed it principally the same way we have designed all of these generations, which is we release it at some fraction of its full capability, and then we improve it over time. So for those who aren't intimately familiar with how we run our first generation, we have two of them, an H1-1 and an H1-2. Yes, we are that clever with our naming. And the H1-1 will be up for a couple of weeks, and then we take it down for a couple of weeks, and then we put it back up for a couple of weeks. And because we have two, we try to alternate that so that there's always one running. But the improvement then goes directly to our customers. And so over the course of time, as kind of evidenced by that, by the chart on quantum volume, you get to see these multiples increases, 100-fold increases in the performance level just over the span of 12 or so months. It's pretty incredible. So I'm not going to answer your question directly about what is the number of qubits, although, like I said, it will be bigger. I will say one thing, which is our first generation, we have an emulator, has a noise model that's very, very close to our actual H1 generation system, and that emulator, well, we don't, could run on a laptop. Our H2 generation, for the emulator, even when we release it, needs a very, very high performance GPU cluster. And this is kind of my favorite part. When you run that GPU cluster, it's actually faster to solution on our quantum computer than it is on the high performance GPU cluster. So we are at that point where we're going to start to see what quantum computers do when they really challenge what classical computers can do as well. It is, by the way, impossible for me to see the audience. So I don't know if anybody has their hand up. Anybody else has their hand up? Yeah, hand in the back. No, maybe down here too? Okay. All right, I'll leave it to you to find the people. Okay.
I guess I should stand. Hi, I'm Bob Hammond, and it seems to me one perspective, I mean, we're all worried about what the limits of quantum computing are versus classical computing. And I think one perspective that's important, and it came up at the end of the conference here last year, Scott Aronson talked for quite a while, basically, and tried to answer hard questions. And I think what perspective is, and he is a theoretical computer scientist. He is worried about basically the limits of classical computing his entire career, and he's made enormous contributions to it. But I think he would say that we really don't understand as well as we'd like the limits of classical computing. And so we look at this new thing now, this quantum computing, well, it's fundamentally different. I mean, it's just fundamentally different. These qubits are really different. And, you know, when Feynman first had the idea, you know, back now 40 years ago, he realized that this is the way to simulate quantum mechanics. It just inherently is strong for that. And we're sitting here 20 years later, or 40 years later, sorry, and we're saying, well, this is the only thing we can be convincing about. That simulating quantum mechanics, simulating quantum materials, simulating quantum chemistry, these are things where these tools will be very powerful. And I certainly believe in that. I'm a quantum materials person my whole career. But I guess I also, I've been trying to figure out for 25 years what the limits of quantum computing are, but a perspective that really doesn't come across here is this is fundamentally different, and there's just really uncertainty about what the limits of classical computing are. Real fundamental uncertainty. And so there's great potential, and we're not going to find out what the great potential is until we actually have machines that work, fault-tolerant machines and get to scale, all of this. And we're going to find out little by little as we go along about this. But right now, we can sit here, just like Feynman could 40 years ago, and say, well, quantum chemistry, is that important? Quantum materials, are they important? They're enormously important. I mean, what's happened in the last 40 years in those areas is just, we could have many meetings about that subject. So anyway, since I haven't seen that perspective come through, that's my perspective, and I really do think there's great potential here.
I guess just two things I will say on top of that. First is, these are incredible systems, and in, I think, human evolution we've seen, when you give brilliant people access to incredible systems, they will find something to go do with them. So I actually have a different expectation about when we start to really see value from these, and it's not all the way till we have fully universal fault-tolerant systems. That we will get there. It will be great when that happens. We're going to see a tremendous amount of progress on the way. I also am really jazzed about the fact that every time there's advancements in quantum computing, it pushes classical computing better. Every time. Like this, sometimes quantum inspired, sometimes because we find more efficient ways to simulate, but we're actually getting a boost to the entire computing ecosystem, quantum and classical, by the progress that's being made right now. So, I don't know. I think it's a very exciting time.